So if you turn this off, you see that the spectrum bounces whenever I talk. And this should be pretty familiar to you. 'Cause I mean, I imagine you see this kind of stuff in clubs or whatever when the lights go with the music. This is just kind of separating that by frequency. So and the reason it takes a long time to drop down is because they've kind of got a filter on each of these, or it limits the speed at which it can change. Of course, we can get rid of that.
It's averaging a bunch of successive FFT or magnitude squares. So it's got a basic, it's like a one-pole filter, a one-pole smoother on the sequence of magnitude spectra.
So you can see that you can see how the spectrum kind of shifts up on the higher note. I'll do that again. Yeah, I didn't plan a singing demo today. This is only half of the FFT. So a couple of the plots that you saw for a sine wave, you had one peak at the negative and positive frequencies. As was mentioned, for all real signals, you're only going to see half of the spectrum. So it's kind of redundant to display both halves of the spectrum. Also, it makes sense to kind of abstract all the math stuff away for the people that are using this, because they don't care about the negative frequencies and so on and so forth. So that's my voice, and my voice has a lot of different frequencies. But say we replace that with a tone generator. It's just lovely. I don't know why that happened. But you see that you get a single spike, just as is theoretically predicted.
Another thing worth mentioning is that you've got a log frequency and log magnitude scale here.
Yes, that's true. So we've only looked at linear scales so far, I believe, but
For frequency.
did we talk about logarithms? Yeah, we talked about
We
logarithms.
did dB.
Yeah. Well, this is in dB, and you can kind of see that. So this is a sine wave, and do you guys remember when we talked about square waves the other day and how you make a square wave using Fourier series? You keep adding in the odd harmonics, and so we can make a square wave right here. Sine wave, square wave. You can hear that it's got a lot more harmonics. It's very rich. And the peaks fall off exponentially. And the reason they look linear is, again, because we're on a log-log plot where the slope of the peak decay indicates the exponential decay in linear space. No need to talk about that quite yet. Just disappears. That's not very informative. We're not going to talk about that. So here we have white noise. It's not really useful to hear it. So on average, white noise is flat spectrum, which means that you have as much energy in your low frequencies as you do in your high frequencies. Here it looks like you have a little more in the high frequencies. I don't really know what that's all about. It could just be a defect of how they're plotting it. Another kind of noise is pink noise, where the magnitude falls off as 1 over f. So now you get that downward slope, just like that if you're looking at it from this angle. And what else is to be said? What am I overlooking here?
This is great.
It's a very unprepared
Can we do a
demo.
side sweep?
Yeah, that sounds like fun. just keep them going.
Substitute right here. So that tail is a function of your analysis parameters.
Yeah. To a degree. So most of the tail, yes, is a function of this analyzer decay thing that I have here. If I turn it on low, it'll just kind of stick around. But also, there's going to be a bit of a smear instead of just a peak, because each FFT frame that is being looked at no longer just has one frequency, because it's starting at a low frequency and working to a high frequency. That shouldn't be incredibly apparent from this, but that is a fact of the math. There's a sweep. I guess we can't do any other kind of sweep, although really there's no reason to. We have a linear sweep. Here's the logarithmic sweep. So it sounds very different. It spends a lot less time at the higher frequencies than it does at the lower frequencies. And you can also see that the peak of it kind of drops off. I don't know if we want to go into quite why that is. It's because it's spending less time at any of those high frequencies. I believe the area underneath of this curve would be the same at any point, at least in logarithmic space.
So when you know how to compute the Fourier transform, you'll be able to predict that this is what you should see. So you'll get to where you know exactly what's happening as a function of your FFT size, the type of window, the kind of averaging that you're using. And if you think about it, you'll be able to predict these various things. And more importantly, when you look at a spectrum analysis, know what's a result of your parameter settings and what's in the underlying signal that you're really going after.
So yeah, because this is a little different than the one that we'll talk about in class, because it's in log space and because it's one-sided. Just to be clear, if this was in linear space, this would start at 0 and it would go up to your Nyquist frequency, which is equal to half your sampling rate, and the negative frequencies would be flipped over. But in MATLAB, when you compute your DFT, it's going to put them in a different order. Instead of having the negative frequencies over here, it's going to stick them over here. So that's just something to be aware of. You fix that with the FFT shift command. Joel?
I'm not sure I have an intuitive understanding of what a negative frequency is. Can you aid me in this understanding?
That's not a very easy question to answer.
Or is it purely mathematical?
Any explanation that I give you would be. Yeah, it is.
Well, you can graph it. So you know, I wrote it down mathematically as e to the j omega 0 t as being a positive frequency, e to the minus j omega 0 t being a negative frequency, single frequency component. Imagine I plotted in a complex plane. So here's a complex plane, here's the unit circle, and at time 0, I'm at 1, which is here. And then let's say we're talking about e to the j omega 0 t. Now let t go. Then we're going to traverse the circle, because e to the j theta is going to go around the circle, right? And so I'm going to be going around at angular velocity omega 0, and I will be going in a particular direction around the circle. So if I now switch from omega 0 to minus omega 0, then I'm going around the other way. So in the complex plane, it's clockwise circular motion versus counterclockwise circular motion. And then you can also see in the complex plane, if you add clockwise and counterclockwise, then you're always going to be matching up. You can cancel the imaginary part and get something real. And we'll see some of that. I'll be actually, when we talk about sinusoids, I'll be showing you plots of circular motion, clockwise and counterclockwise, adding together to give you a real sinusoid. We have some nice graphics on that.
That may or may not help you. I find that it's best to just leave it as a mathematical construct, because trying to think of a negative frequency it doesn't make a whole lot of sense. I don't know if you agree with that statement or not.
Well, I think it becomes friendly if you think of it as an angular frequency in the complex plane. So the positive frequency really is a counterclockwise angular frequency around the unit circle in the complex plane. And the negative frequency is a clockwise angular frequency around the unit circle in the complex plane. So you really do have to embed your thinking in the complex plane to distinguish positive and negative frequencies, because in the case of a real sinusoid, if the phase happens to be 0, then cosine of omega 0 and cosine of minus omega 0 t are exactly the same. There's no difference. But sine flips it, sine of omega t flips its sign when you go to negative frequency. So cosine's unchanged and sine inverts when you negate frequency. And so it's really only the two of them together that can be used to understand negative frequency. And so the two of them together are most naturally plotted in the complex plane as the x and y components of circular motion. And we'll be seeing that, because I haven't even really introduced sinusoids, really. Next week is when we really introduce sinusoids and exponentials, and I'll do all the graphics. We're going to look at that S-plane and the Z-plane. And S-plane is sort of the complex plane for continuous time signals, and the Z-plane is the complex plane for discrete time signals, and we need to go back and forth between them when we go from digital to analog and that sort of thing.
I don't know if there's anything I mean, this whole talk was kind of the spur of the moment, but is there anything someone wants to see on here or anything to mention?
Do I have a book with me at some point?
Sounds like you.
Is there a book on your computer?
Yes.
I just want to show one thing. I just want to show one thing.
Okay. I'm good with that.
The cover of the book is this subject. So over here is the complex plane where you had circular motion, and if you project it, down to the real axis, you get a cosine. And if you project it to the imaginary plane on the imaginary axis, you get sine. So this is the graphic that shows you that. It's inside the book as well, but
The Wikipedia one that's not kind of cropped to fit on the cover of a book is a little clearer to look at.
yeah, but it's on the cover of our textbook. It's worth noting that it's there. Yeah, let me go ahead and just jump ahead to a couple of the graphs. That one's exponentially decaying. And I have some animations of this stuff too. There it is in more detail. Just see, I think I have something more elementary back here as well. It's somewhere. So e to the j omega t goes around the circle like that. I need a pointer. The most narrow thing I can find. Oh no, I've got a pen. Right, so e to the j omega t goes around, if t is 0, it's here, and then as t grows, it goes around and around like that, right? And now if we just let t be this axis, then we get this helix, okay? So that's e to the j omega t just kind of stretched out through time. And so if we now project onto the floor, we get cosine. That's the real part. And if we project onto the wall over there, we get sine. That's the imaginary part through time. So this is the projection of the vertical axis, the imaginary axis, and then stretched out along the wall to see what it does. And then the real axis is here. Project that down to the floor and let it go through time. And you get your cosine down here, your sine up there. It's Euler's identity once again, but where theta is omega t. So this is a real sinusoid. This is a real sinusoid, the projections, and then the two of them together make a complex sinusoid, an e to the j omega t type sinusoid. And it's got a particular chirality. It's got a particular twist direction. And so this is the positive frequency sinusoid. Remember, it's the only single frequency sinusoid kind of. This helix is the only true single frequency sinusoid. And to really make it that way, it has to go forever to the right and it has to go forever to the left. It can't just turn on and it cannot turn off. Those would create frequencies all over the spectrum. A turn off or turn on transient is an infinitely wideband event. It goes forever, like a sync function. Sync function, the spectrum rolls off as 1 over omega. You might even remember when we talked about windows. Any discontinuity, any step discontinuity in a signal gives you a 1 over omega roll-off, meaning that it's non-zero to infinity. Now, you might worry about that. Well, wait a minute. Isn't infinite frequency infinite energy? Doesn't the universe end as soon as that happens? Well, no, because if you sum 1 over omega squared, so you have to square it to get power or energy, and then you integrate, that's finite. So you have finite energy, but infinite bandwidth, truly infinite bandwidth. If something turns on, if something turns off, you have infinite bandwidth. And that's why there's no such thing as a perfectly band-limited system, but it's close enough if it rolls off fast enough. So I just want to emphasize that the only single frequency function is this helix going forever to the left and right. And it can twist one way or the other way. So this is the counterclockwise case, and we're just arbitrarily calling that the positive frequency case. And then when it's spinning around the other direction, that's what we define to be the negative frequency case. So you could say it's so positive versus negative frequencies is just arbitrary assignment to right-handed versus left-hand corkscrew. We have two cases, we have to label them. We want frequency to be the density of these lines in here, right? So omega, as omega goes up, these get more densely packed, it becomes a more, high frequency spin, because this is the time axis here. So, and amplitude is the radius, is the excursion of that thing. So we need both directions. And the reason we need them is because we need to add them together to get real sinusoids. So what we really want to do is build up these oscillations like the cosine down here and the sine over here. These are what we observe in nature. This is what happens when you strike a tuning fork. This is what Daniel Bernoulli recognized as the fundamental components of all vibration. And it has a big history, and it's been outrageously successful. This is our basic laser photon. In physics, it's unbelievably huge, right? I mean, this is also the mathematical foundations of the standard model in physics. So, does that make positive and negative frequencies a little more friendly?
Yeah.
All right. And here it is in the cover. Yeah, so we have a lot to say about sinusoids. Here's that example of the graphical representation that I mentioned. Cosine, sine, this would be rotated, multiplied by j, added. This is showing how you can take sine, cosine, and then sine, and then j sine times sine, and sum them to get e to the j omega t, e to the j theta. So it's Euler's identity depicted graphically. That if you add this graph and this graph, you double the positive frequency component and you cancel the negative frequency component and get a pure e to the j omega t. So it's just kind of a graphical calculator. And then after that, we'll go into exponential decay. Here's an exponentially decaying sine wave, and it will be the nearest to single frequency case will be decay like this. And this is now the building block of all linear systems. And then we'll get to the S-plane and the Z-plane. S-plane is for continuous signals, and the Z-plane is for discrete time signals. So we'll spend as much time as we want talking about those, because we want to get really comfortable with the S-plane, really comfortable with the Z-plane, because that's where everything happens in like filter design and system representations and signal representations as well. But it's especially important in linear system design and development and interpretation, manipulation. You need to be comfortable over the complex plane. So all your analog filters live over the S-plane, and all your digital filters live over the Z-plane. And they're both complex planes, but they have their own conventions. So that's where we're heading next week, and then we'll do some software associated. Any last questions before we go off and get some food? Come back, concert at 7:30. Or like me, go into a sequence of meetings and just barely make it to the concert and just eat a peanut butter bar that's in your bag. Yeah, I don't get to go eat today. Unless one of my meetings wants to go eat. If it's you, suggest that.
Julie's?
Yeah.
I just wanted to talk about, I'm thinking about declaring finally. I was trying to figure out really my advisor should do. I'm looking at.
Office hours tonight, 7 o'clock, 9 o'clock upstairs in the seminar room.
Also music science and technology.
Actually, that does sound bad, doesn't it?
So
I
you're
think
thinking,
you know a lot of people or.
If you want to come to office hours, just email me or something, otherwise I won't be there.
or music majors.
And I'll probably still try and reschedule to tomorrow or something.
With the master's,
No, not last year.
so you're an undergrad and you're
My idea is to go.
And then in the lead, okay, once that's cool. Well, I can certainly be an interest from the east side. Well, it's just my past. So I mean, it's in the music department, and I got a courtesy appointment. So I can be there. So I'm happy to, but I'm more comfortable with finding something that really flavored stuff. Like, I mean, the music side.
I don't know if you're not
It's better represented by, other music faculty, whatever those requirements are. Although the MST component,
There's no way all of these are.
My impression is that the MST is a little bit separate from like it's hard to do theory and a little bit of history or after that.
it just has a couple of courses. Yeah, if you take a couple of common courses, you get an MST, adjective attached to your music degree. So, I think you might need, I assume you say that, and vice versa, that leads are necessary. But, here, this is he's working on that, I believe, you might talk to him, because he would know if it's okay for me to.
To watch.
Yeah, so you might ask him, if that's okay, I'm happy to do it, I'm very happy with it, so, and I know it requires an MST component of you. I can really do either side, but for the MST component, more than any of the way from, right? 15 that we from here, so. Sure. What's your name? Brendan. All right, you sent an email. Good, good. All right.
Yeah, so basically, I just figured out my interests and I really focused around yeah, so I'm really interested in the core thinking basically, where I'm really interested in the idea of pushing
Great. Excellent. A lot of people here who would like to work with you on that. We all care about that.
Yeah, so I don't know enough to know where
What are the issues? Right.
from the microphone system.
Right. Yeah, let's start with Jake Hayes, who teaches our recording courses.
And that's only
Musical acoustics. Yeah, that's a very interesting.
So it should be this plus.
That sounds good, and I'm happy to, sign anything and, whatever they say is okay. All right,
Turn it
that's
into
good.
a heat sink.
You waiting for a question?
I would put it on Eddie's desk and just make a note that you know.
I'm here till,
I would just sit down and wait, this is more of a conversational thing.
Yeah, how about after all this? Quick question. Okay. And what's your name again? Mark, okay. Question? I thought I saw a question about to happen.
Yeah, grab a chair.
It's a homework problem?
Yeah, so first I had a riddle question.
Okay.
Discussion.
Well, it's not a homework question, but it's basically what we talked about in class.
Uh-huh.
Finishing up the visa.
Applying the two.
If I get too
Oh, that's,
complicated, I'll just try to use the answer.
yeah, make sure this is up.
Yeah, otherwise, if I really feel like I need the hands-on attention, I'll.
Yeah, shoot me an email when we meet up. Don't turn in half-done crap. Turn in stuff that you're happy with when it's convenient for you.
Yeah,